So today we're going to put together the things that we know about sinusoidal functions, y equals sine x and y equals cos x, with transformations that we know from quadratic and exponential functions. So I'm going to be doing this on Desmos, and your best strategy is to open Desmos on your device as well and do this with me as I go. The instructions on my slides are about graphing calculators, and some of the process is the same, but I am going to be using Desmos. So the first thing that I'm going to do is put in y equals sine x and compare it to y equals 2 sine x. So the graph of y equals sine x from yesterday is we notice that y equals sine x has a maximum value of 1 and a minimum value of -1. Sine starts at 0, 0, and it does one complete cycle in 360 degrees. What we would like to add to this today is what happens if I have a transformation. I have a 2 sine x. What happens? And as we expect from quadratics and exponentials, is that I have a vertical stretch factor 2. This one goes twice as high and twice as low as the original y equals sine x. The next one that I'm going to have a look at is y equals negative sine x. From our understanding from functions before is that a negative is a reflection. And this is outside at the front of the function. It will be a vertical change. So a vertical reflection should be upside down. So y equals negative sine x. There. The red one is the original. The blue one is upside down, a vertical reflection as we expected. C, the third investigation that we're looking at today is y equals 1/2 sine x. So just as before, this is at the front of the function outside of the x value, so it should be a vertical change. A vertical compression factor 1/2 is what I'm expecting to see. I expect it to be half as high as the original function. All right, so my original function is sine x, and if I have a half, there, the blue one is half as high and half as low as the original function. So my transformations are the same as other functions, just change that amplitude. It is only up to 1/2 and down to -1/2. The next set of transformations that we're going to look at are when I add or subtract a number at the end of the function. When we did that to a quadratic, that was also a vertical change because it's away from x on the outsides of the function. I expect this would be a vertical translation up or down. So if I have y equals sine x plus 4, it moves the entire function up 4. The second one that we were going to look at was y equals sine x subtract 4, and that moves the function down 4. So the transformations that we've looked at so far today are both vertical. Now we're going to look at horizontal for just a moment. Inside the brackets with x, I have a change. Y equals sine bracket x minus 60. I expect that to be a horizontal change. With x subtract 60, it should be a horizontal translation left or right. And horizontals are always different than they appear. I expect y equals sine x subtract 60 to be a shift to the right 60. Y equals sine bracket x subtract 60. There it is. 60, 3 squares to the right. If I had x plus 60 in brackets, it should be 60 to the left. And I've taken that red one and shifted it 60 to the left. It is as we expected. So in summary, the very same translations that we've had on other functions, if I have an a value at the beginning, at the front of my function, that's going to be a vertical change. It's being multiplied, so that will be a vertical stretch. If A is less than 0, it's negative, then we have a reflection. A vertical reflection means things are upside down. If A lies between 1 and 0, so we're going to just ignore the negative part now. We're just going to talk about the absolute value of A. But if it is a fraction between 0 and 1, it will be a vertical compression. So it's going to be flatter. But in this unit, a helpful word can be that the amplitude, which is usually 1, amplitude, sorry, I can't spell. Pretend that says amplitude. My amplitude is A, whatever that A value is. If A, ignoring the negative, but just the absolute value of A, if it is greater than 1, so a large number, then we have a vertical expansion. We tend to use the word stretch, factor A, so it's going to be twice as high or 3 times as high. But the big idea is that the amplitude both up and down from that axis, that middle place, is A. The other vertical change is that plus C on the end. At the end of the fraction, if we are adding C, we are moving the entire function up C. If we are subtracting C, we are moving the entire function down C. And lastly, inside the function in with x, we have a horizontal change. These ones are the tricky ones. So if I have x subtract 5, that's where I have 5 to the right. If I have x plus 5 inside the function, I have 5 to the left, backwards to how it appears. The other foundation that you need to have at your fingertips, and we'll have ones up on an anchor chart, is y equals sine x, y equals cos x. Just that basics so we can do the transformation. So y equals sine x starts at 0, 0. That's the big idea. Its highest is 1, and its lowest is negative 1. So it goes from 0 to 1, back to 0 to negative 1, back to 0. And the period for that is 360 degrees. So in the middle, I know I have 180, and you can subdivide from there in order to move it. Y equals cos x, very, very similar. Highest is 1, lowest is negative 1 before the transformations. But it starts at the maximum, and it passes through 0 to the lowest 0, back to the maximum. So its curve looks like a sine curve moved over, and it does that cycle in a period of 360 degrees. Oh, please do yours a little smoother than mine, but its amplitude is 1, and the halfway point would be 180, just as a good reference. The zeros are at 90 and 270. So we've got those, we've got our transformations in mind, and we are going to graph a few. The first one that I'm going to graph today is y equals 2 sine x plus 4. So my thinking is, what is my parent function? It is y equals sine x. So I'm going to draw the basic one first and set up my axis so that I can move it. So I know that sine x starts at 0, 0. I know its highest is 1 and its lowest is negative 1. It has an amplitude of 1. And I know that cycle happens in 360 degrees. I have lots of space here, so I am going to have 90 degrees every 3 squares. So I'm just going to set this up. It would be really helpful if you paused and set one up for yourself so we can draw this together. Y equals sine x starts at 0, 0, goes to 1, back to 0, to negative 1, and back to 0. Then I have transformations, and it is always best to work from left to right because that means we do our multiplications before we do our additions, and BEDMAS is the way we need to draw this. Y equals 2 sine x would be my next transformation. That is a vertical stretch factor 2. So all my ups are doubled. So from 0, 0, I go twice as high. My amplitude is now 2. Zeros stay, because multiplying a 0 by anything stays the same. My amplitude is 2, so I go to negative 2. There. So I should have a curve twice as, well, not too bad. There. The last transformation is that vertical translation for up. Y equals 2 sine x plus 4. So that means every point is moved up 4. A nice way to do this is to say, you know what? If every point has been moved up 4, then that axis, which is usually right along 0, is now at 4. So, and I'm going to run out of room, but this is now the middle, the axis of symmetry for this function. I'm going to move the blue one up 4. So that is my starting place. 2 above 4, so I've not planned as well as I should have. Back to the midline at 180. 2 below the 4 at 270. And back to 0 at 360. So my curve is 4 higher, but it still has an amplitude of 2. And continues there. Let's do 2 more together. All right, for this one, I first see that my parent function, my starting function is y equals cos x. So I'm going to draw that first. Cos starts at the maximum, and my maximum is 1. This one, I am not doing any vertical stretches, spoiler alert, so I can spread that 1 and negative 1 out and have lots of room. Cos goes from highest back to highest again in 360 degrees. So I'm going to have my 90 every 3 squares again. I also know that I'm going to shift at 30, so I'm kind of cheating a little bit, but I would like to have 30 as exactly 1 square so it's easy to shift. All right, cos has an amplitude of 1, starts at a maximum, ends up back at that maximum in 360 degrees. My minimum is in the very middle. So I kind of mark those key points and I curve as smoothly as I am able. There. Then I do, in order from left to right, my transformations. The first one is negative. And that negative is at the front of the function. It is a vertical reflection. A vertical reflection means the ups go down and the downs go up. So a vertical reflection. So instead of starting at the maximum, I'm going to start at the minimum. Instead of going down, I'm going to go up to my maximum in the middle and my minimum back at the 360 mark. As smoothly, so not jagged like saw teeth, but smoothly, I go from minimum to minimum in 360 degrees. The last transformation is that plus 30, which is in brackets. That means it's a horizontal change, and horizontal changes are always a little bit painful. So we are taking the blue one, horizontal translation. It will be 30 to the left. All right. So 30 is 1 square. So I'm going to take my main points and move them 1 square to the left and join with a smooth curve if possible. And I have my final function. Last one. y equals 3 sine x minus 60. So my thought process the same is my parent function is y equals sine x. I am going to set this up knowing that sine starts at 0, 0. It has an amplitude of 1 and it does a complete cycle in 360 degrees. So I'm going to make the same markings, 90, 180, 270, 360. My curve goes from mid to maximum, to mid, this one's not as smooth, I'm sorry, to minimum, back to mid. And that is y equals sine x. Working from left to right, we would do our vertical expansion or stretch factor 3. So that means all of the ups and all of the downs are tripled. So my first transformation takes me from 0, 0 to 3. My amplitude is 3. And to negative 3. So from 0, 0 up to 3, back to 0, down to negative 3, back to 0. So it's going to look very much stretched vertically. There we are. Last is I have in brackets x minus 60. So in brackets means it's a horizontal change, and I have a horizontal translation, 60 to the right. So this entire green function is moved 2 to the right, 2, 2, 2, 2. But I shouldn't leave a little gap at the front, so I'm going to join this as smoothly as possible. And then say, hey, don't leave this part at the beginning. So we'll just have our curve start like so, just to fill it in. Okay, we're going to try some on our own.